so let's look at the first question. It says the diameter of bolts produced by certain machines are normally distributed with the mean of 0.3 inches and a standard deviation of 0.01 inches. What percentage of bolts will have a diameter greater than 0.32? So when you see a question about percentage, percentage or probability or area, those all correspond. So it's really important to first draw your curve. It says it's normally distributed, so you're going to draw your normal curve. You're going to write in your mean, which is 0.3, and write down your standard deviation, and your standard deviation is 0.01. So what percentage of bolts will have a diameter greater than 0.32 inches? Well, we're looking over to the right of the mean. And so your probability is going to be less than 0.5. And we are going to use the calculator to calculate these probabilities. You can use your z-score table if you'd like. So what was the command that we used in order to find area? So inverse norm uses area and gives you z-scores. So which one was it? And this is the sigma. So it was the other one, right? So it was normal CDF. So this is a question from chapter 6. We're looking at our area starts at 0.32. Then we go up to a very large value. So let's put 10,000. And this is obviously not a standard normal distribution because we have a mean of 0.3 and a standard deviation of 0.01. And so we're going to put in that next. Our mean is 0.3. Our standard deviation is 0.01. And so our calculator will convert those values to z-scores for us. So go to second vars, go to normal CDF, put in the lower value of 0.32, an upper value of 10,000, and any large number will work there. Our mean is 0.3, and our standard deviation 0.01, and that will give you an area of 0.0228. And remember, when you're giving these probabilities, you always give 4 decimals, but over here it asked us for a percentage, so you have to take that probability and change it to a percentage. So move the decimal point 2 places to the right, and so that corresponds to 2.28%, which is answer D. So just understand percentage, probability, area, those correspond to each other. Obviously, when you're changing it from probability to a percentage, you have to move the decimal point, but the same type of problem. All right, let's move on to number 2. If you guys do have questions, ask questions. Yes?
Are you going to give us the D4 sheet for our testing?
I'll have some extra ones. If you want to use the z-score table, that's fine. All right, so let's go to number 2. It says, how many business students must be randomly selected to estimate the mean monthly earning of business students at one college? We want 95% confidence that the sample mean is within 135 of the population mean, and the population standard deviation is known to be 538. Okay, so we're trying to estimate a minimum sample size. Let's write down all the things we have given. We have 95% confidence. We want the sample mean to be within 135 of the population mean. That's actually our margin of error. Because remember, we have our starting value, which is our sample mean. We're going to find that margin of error, and that's what we add and subtract in order to get our confidence interval. And then the population standard deviation is known to be $538. Okay, so to find our sample size, and you are allowed the formula sheet, which is that last page on the Chapter 7 handout. Okay, so looking at your sample size, you have the formula N is Z alpha half times sigma divided by your margin of error and all that squared. 95% confidence, that's actually one of our most commonly used ones. So we actually have that listed on that chapter handout as well. But if you have some other percentage, you can find the z-score that corresponds with 95%. Remember, you have 95% in the middle, so 0.95 in the middle. That leaves you with 5% in the two tails, or 2.5% in each tail. And then you simply add the two areas on the left together, so 0.975, and then you use the inverse norm of 0.975. And what is that? And inverse norm, again, same place where you found the normal CDF, so second vars, inverse norm of 0.975, bless you, is 1.96. And you always give those z-scores to 2 decimals unless it's one of the, the ones with 3 decimals, such as, the ones listed on your special formula sheet, the 90% and the 99%.
Can we use both table sheets on the test too?
Yes. Yeah. So you can find these z-scores obviously on your table. Generally using the calculator is a little quicker, but table works as well. So.
Sheet as well with the equation sheet?
So this pretty much summarizes all the formulas for Chapter 7. I think Chapter 6, all you need to know is the normal CDF and the inverse norm. I think you can memorize, which one is which.
Can we write on that?
I think you're okay.
Okay.
I think that's good enough. So let's plug in what we have. So we just found the critical value, which is that Z alpha half, right? That's the one that has alpha half to the right, which is the 0.025. So we have N is equal to 1.96. We had our standard deviation given to be 538. Our margin of error is 135, and then all of that squared. And then also remember, for sample size, this is the only formula where we always round up, unless it tells us to round. So look out in your homework how it says. So 1.96 times 539 divided by 135, and then that number squared is 61.01. And even though it's super close to 61, you still round it up, and the answer is 62. So read carefully in your question and look what are they looking for, right? They're looking for a sample size. We had formulas for sample sizes, either for the proportion or for the mean. So again, you have to look at the wording carefully. Make sure you understand what your margin of error is. So if it says we want to be, 95% confidence to be within 135 of the population mean, well, that's your margin of error. So make sure you understand what is what, label everything in the question, and then put it together to find your sample size. All right.
Is it going to be multiple choice?
It is not a multiple choice, no. But there's only, I think, 10 or 11 questions, so it's much shorter than this, so you'll have plenty of time. I just wanted to put a number of questions on there. But no, it's open answer. So that's why it's important to understand what the question is asking and to do it correctly. All right, so for the next one, it says use the given degree of confidence and sample data to find a confidence interval for the population standard deviation sigma. So it tells you this is what we find our confidence interval for. So don't use the information and find a confidence interval for the mean when it asks you to find one for the standard deviation, right? And standard deviation was the one you had to manually calculate, so it's the one that's a little more complicated. You do have to use the table to find those chi-square values. It says assume that the population has a normal distribution. Round the confidence intervals to the same number of decimal places as the sample standard deviation. So follow the directions, do the rounding correctly. So the mean replacement time for a random sample of 20 washing machines, that's our N, is 10.9 years. Okay, that's our mean. And the standard deviation is 2.7 years. Construct a 99% confidence interval for the standard deviation sigma of the replacement time of all washing machines. All right, so we're going to find the margin of error. We're going to find the left. Well, actually, we're going to find the left chi-square value and the right chi-square value, and then we're going to put it all together. Okay, so the formula for finding your confidence interval, we have these n minus 1 times s squared divided by the right chi-square value squared. And then since we're estimating the standard deviation, we have to take the square root of that. This is less than sigma, which is less than n minus 1 times the standard deviation squared divided by the left chi-square value. And all that, again, this square root. Okay, so our chi-square values depend on our degrees of freedom. So if our sample size is 20, what are our degrees of freedom? 19. Okay, and then it also depends obviously on our confidence level over here. So we have 99% confidence level. We have a right skewed distribution, which gives us, not symmetric values like the t distribution or the normal distribution does. Bless you. But we have our left chi-square value over here. We have 0.99 in the middle, which leaves us with 1% left, or 0.5% in each tail. So 0.005 on the left, 0.005 on the right. And on our chi-square distribution, the chi-square distribution always uses the area to the right of the critical value. Okay? So to find the right chi-square value, we're going to look for 0.005 in the right tail. So that's over here, the last column, 0.005. And then going down to 19 degrees of freedom, we have a right chi-square value of 38.582. So that's the right one. The left one, we have to add these two areas to find, in order to use the area to the right. So that's 0.995. And remember how those columns go together. They always add up to 1. So our very right column actually goes with the far left column over here of 0.995. So this is our left chi-square value. Going down to 19 degrees of freedom, we have a left chi-square value of 6.844. Okay, so remember to use the degrees of freedom, and you have those corresponding columns. So the first column goes with the very last column. If you have, 0.5% over in the right tail, you're going to have 0.5% in the left tail, and that goes with a 99% confidence interval.
How did you find the left tail?
Okay. So let's go over this again. So the first and the last one do correspond because those probabilities add up to 1. Okay, but on looking at my curve over here, a 99% confidence means 99% in the middle, which leaves 1% in both tails. So then you're going to split that in half, which gives you 0.5% in each tail. So we have 0.005 on the left and 0.005 on the right. So when you're finding this left chi-square value, you're going to have to look at the area to the right. So you have to add the 0.99 plus the 0.005 in the right tail. And that gives you an area to the right of this left chi-square value of 0.995. So then you look at the column which says 0.995 to the right and go down to 19 degrees of freedom. And that's how you find the 6.844. So that's why I said, if you find the one column, the other one is going to be the corresponding column. So those two numbers on the top are going to add up to 1. So let's plug in n minus 1 is 19, that's our degrees of freedom, times s squared is 2.7 squared, divided by our right chi-square value, which is 38.582. And remember that value is already squared, so you do not want to square that value again. Okay? On the other side, we have 19 times 2.7 squared divided by the left chi-square value, which is 6.844. And then we will put all this in our calculator. So we're going to take the square root of 19 times 2.7 squared divided by 38.582. And that gives you a left value, and we're rounding to 1 decimal, just like our standard deviation was rounded. So we have 1.9 on the left, which is less than sigma, and then we're going to calculate the right side. So again, take the square root of 19 times 2.7 squared divided by the left chi-square value, which is 6.844. And then calculate that, round it to 1 decimal, which is 4.5. So over here, it looks like our answer would be C. So this is the one confidence interval that we have to calculate by hand. All the other ones, we can calculate the margin of error and do it manually, or we can use the calculator command. But for standard deviation, it's the one you have to do manually. So make sure to look over the examples. On our package, there's a couple extra ones that we didn't go through, so you can practice a little extra there. All right. Okay, for number 4, the following confidence interval is obtained from a population proportion. So our confidence interval goes from 0.688 to 0.724. Use these confidence interval limits to find the point estimate p hat. So we have a confidence interval given. We're trying to find the p hat. Where is p hat located in relation to our confidence interval? Anyone? Where? Okay, here's my confidence interval. Where is our point estimate?
In the middle.
Middle, exactly. So how do we find it when we have a confidence interval given? Take the mean of the two values. So the upper limit plus the lower limit divided by 2. So 0.688 plus 0.724 divided by 2. So that's 0.688 plus 0.724 divided by 2 is 0.706, which is 8. So it's very easy, exactly. So it's right in the middle. Remember, that's how we build our confidence interval. We start with a point estimate, we find our margin of error, and then we subtract and add that value to get our confidence interval. Okay? All right, number 5. Okay, so a study of the amount of time it takes a mechanic to rebuild the transmission for a 2005 Chevrolet Cavalier shows that their mean is 8.4 hours and the standard deviation is 1.8 hours. If 40 mechanics are randomly selected, find the probability that their mean rebuild time exceeds 8.7 hours. Okay, so this is actually one of the Chapter 6 problems. And this is the central limit theorem at work over here. So what we have is we have a normal distribution, but instead of just looking at, you know, the hours for one person, we're going to look at the mean time of 40 mechanics put together. So what happens to the normal distribution? Yes, it gets squished together. So it's, and what was our x, actually our mean of our x bar? You're thinking the standard deviation, right? So our mean of these mechanics, let's write down first the mean, is 8.4 hours, and the standard deviation is 1.8 hours, okay? What is the new mean? What's the mean of our sample means? It's the same, right? So it's 8.4 hours. What's the standard deviation of our sample means? It's the standard deviation, so 1.8 square root of